The final step in this method is really crucial. You need to violently fling it into the chip tray. Hello Internet, my name is Quentin and this is Blondihacks. Today I'm going to show you 4 ways to make bolt circles, all with varying trade-offs of precision, efficiency, and how much tooling you have to own to make them happen. So let's go. I've made up some sample discs to put some bolt circles on. We're going to do a 3/4 inch circle on each of these. There's lots of reasons you might need a bolt circle: pipe flanges, cylinder heads, wheels, all sorts of stuff. I'm going to be showing you small sizes since that's what I do here. Now, let's get the obvious and easy one out of the way first. We're going to do the first bolt circle on the DRO. Step 1 on this method is we need to get the spindle centered up on the center of the bolt circle that we want to create. There's lots of ways to do this. I'm using the dial test indicator in this case on a spindle mount, but you can use a coaxial indicator, you can use an edge finder in a pinch, lots of ways to do that. Once I'm centered up, I've zeroed the origin on my DRO there, but you don't have to put the bolt circle on this origin. Generally, DROs are also going to allow you to set a local offset for your bolt circle from the 0 on your absolute scale. This is useful, for example, if let's say you're making a model steam manifold where you need a row of pipe flanges, each with their own little bolt circle, you can easily offset all of those from the first one with a single setup. The details of this are going to vary a little bit by DRO, of course, but on this one I've got a graphical menu here, so I'll use that to start my bolt circle. And the options are going to be similar on all DROs. You're going to have often the coordinate center of the center of your bolt circle. That's that local offset that I talked about. I'm going to leave this at 0 since I want the bolt circle right where I am now. So I'll skip over those. Then of course somewhere you're going to need to set the radius or sometimes diameter depending on your DRO of the bolt circle. That's to the center of the bolt holes. Since I'm doing a 750 diameter, I'll set that to my 375 radius. A lot of DROs will have a starting and or ending angle option. This is an interesting one. This option allows you to rotate the bolt circle. An unrotated bolt circle is what's typically called a type A circle in the literature, and that's what we're going to show here. But if you set a starting angle, you can rotate the entire circle to another position. You don't usually need to do that because the orientation of the bolts doesn't generally matter. But one example where it might is if you're doing the cylinder head bolt pattern on a steam engine, you need to orient the bolt circle to miss the internal steam passages in the cylinder casting. So that's an example where you'd want a starting angle. If you have an ending angle option as well, that allows you to do an incomplete circle. You can take the number of holes and squish them into a pie wedge and do an arc of bolts. The details of how to set these angles vary by DRO, so your best bet if you want to use them is to set how you think it works, check your manual also, and then do a dry run. Put a Sharpie in your drill chuck and dab a dot on each of the hole positions where the DRO tells you to and make sure it's doing what you think it's doing. Next, of course, there's always going to be an option for the number of holes. I'm going to do a 6-hole pattern in all these examples. It's a very, very common one, probably the most common hole pattern. Now, after this, the options are going to vary a lot by DRO. This particular DRO has options for depth and plane of the hole pattern. For example, if you have the head rotated at 90 degrees, you can do a bolt circle on the side of a part in the YZ plane. And I've never used that feature. I'm always using XY. But there's other options that you may encounter, and you're going to have to check your manual for how those all work. Quick aside, if you have one of these more typical LED display DROs, they are a little bit more like programming an 80s VCR, but not much different than what I've shown, and I have covered bolt circles in detail on this style of DRO in one of my mill skills videos, which I will link to at the end of this one. Once all your options are set, your DRO will have a button to push that will start the sequence of bolts. In this case, because it's a graphical DRO, it shows me the bolt circle that I've programmed, and it's showing me a dot on the hole that I'm supposed to go to next. And what will be common to all DROs is you'll have an X and Y coordinate, whether it's graphical or not, and this coordinate is telling you how to get to the hole. So your job as the humble manual operator is to move the table slides to zero out that coordinate position. It's setting a little local origin on each hole as you need to get to it. So the little red dot is where I am now, and I move it over, and as I'm moving the slides off camera, I'm zeroing out these values. And once those are at 0, or close enough, I'm now positioned over the hole to drill. At this point, choose your weapons as far as your sequence of tooling goes. I'm going to spot each one with a center drill, and I'm going to do clearance holes in this example, so I'll spot them and then drill them all out. Now, at this point, you could start cycling through your tools, drills, taps, reamers, whatever you need. However, with the DRO method, a big advantage is that it's very easy to cycle through all of the holes, and you don't lose any accuracy by doing this. So instead, I'm going to advance to my next hole, and you can see it's giving me a new coordinate set there now to zero out. So I set that to 0, translate to the new hole, and I'm going to spot that hole again with my center drill. So what this allows me to do is iterate through the entire hole pattern with each tool and do minimal tool changes, which is usually a lot more efficient if you can do that. Especially if you're doing a lot of tools, like if you're pilot drilling and reaming or drilling and tapping and so on. Because once I get to the end of the hole pattern, I can hit next, and it's going to take me back to the start, and I can just iterate through this pattern as much as I want. The DRO doesn't care. This is the only method of the ones I'm going to show today where you can iterate through the pattern as many times as you want with 0 loss of accuracy. There's some other methods where you can get close, probably close enough in some cases if you're skilled, but this method is really idiot-proof as far as iteration and accuracy. You can also go back and forth in the pattern. Because it's a DRO, we don't have to worry about backlash. So if you want to go back to the previous hole because you forgot a step, or you want to do the holes in a different order, you want to go across the part, whatever, it's no problem. You don't have to do everything in a particular order. And that is it. That is a very nice hole pattern made with a DRO. That is by far the easiest and definitely the most accurate of all the methods I'm going to show today. So if you have a DRO, honestly, just use it. But let's say you don't. Method number 2 is slightly lower tech. We're going to use the rotary table. I've got another blank ready. And if you don't have a DRO, but you do have a rotary table, then this is also a very accurate method. And now it's a lot more work to set up. Rotary table setups are a lot of work in general. You have to center up the rotary table on your spindle, and then similar to the DRO, we need to center up the part on the rotational axis of the rotary table. In this case, I'm doing that with an oversized mounting hole in the center and a little tapping with my DTI to get that running concentrically. So once again, on the DRO, I have centered my spindle, and I'm going to be using the DRO for translation, but you do not have to have a DRO for this. At this point, we need to translate either axis to the radius of the bolt circle. Doesn't matter which axis, just pick one. And again, I'm using the DRO, but you can absolutely just do this with your hand wheels. The nice thing about the rotary table method is there's no risk of problems caused by backlash in your hand wheels, because you're doing exactly one translation in one direction, and then you're never touching the table again. I've chosen to do my offset positive Y, so my first hole is going to be at the top of the pattern, and I will once again spot that. Now, however, I am going to change tools. With the rotary table method, I prefer to cycle through all of my tools on each hole before moving on to make sure that I maintain accuracy. If you're good with a rotary table, you can iterate through the holes once with each tool, but it's just less error prone if you don't make yourself do that. It depends. I might do the cycling method if tool changing is really expensive. For example, when switching between a short drill and a long reamer, you have to move the head a lot, that sort of thing. It's going to get more expensive to change tools, and it might be worth it. But after that hole is finished, then I'm going to rotate by the angle between 2 bolt holes, which for a 6-hole pattern is of course 60 degrees. And I want to do this carefully because I don't want to get into the backlash in the rotary table. Rotary tables of course have backlash just like any other moving slide. So I'm being very careful to advance to exactly 60 degrees and not overshoot it so that I don't get into backlash. If you have to change directions, then you're going to have to crank past where you want to be and come forward again to cancel out the backlash, just like any other table slide. So the best thing to do is just be very careful on the rotary table moves and stay out of your backlash. That's it though, another very nice looking bolt circle. The rotary table method is a lot more work to set up than the DRO, a little bit slower to execute on, but the result is frankly almost as good as the DRO, just as good if you're good with a rotary table. If you don't have a DRO or a rotary table, however, we can go a little lower tech. We can go old school. I'm going to show you 2 methods for doing this with traditional layout. I've got 2 more samples. I'll blue them up, as you always need to do for layout. I recommend die-cam for this, not Sharpie. Sharpie is not very durable, and we're going to be subjecting these to quite a bit of abuse. As with any layout technique, we need a way to determine the hole positions. Your best friend in this regard is, of course, Machinery's Handbook. In it, you can find all of the math for calculating where each bolt circle goes. And this is a pretty straightforward process of similar triangles. It's junior high school trig. I'm sure you can all do it. And if you want to learn the math, feel free to read up on it in this book and it'll show you how to do it. However, if you don't have to do the math, don't, because over on the next page, you'll find a whole series of tables where they've pre-calculated all of the offsets for all of the bolt patterns that you might ever need. Machinists love tables, and for good reason. Doing the math doesn't make you smart, it just introduces new sources of error. So if you don't have to do the math, don't do the math. Learn the math if you're interested in it, but when you just want to get the job done, use the tables. So these tables are all unit circles, so they give you the hole positions for each hole, assuming a radius of 1. So you multiply that by the radius that you need. The units don't matter, it's just numbers at this point. Another option that we have nowadays is to use one of the online bolt circle calculators. If you just search for bolt circle calculator, you'll find 100 of them. They're all fine, they all work great. It allows you to punch in all of the properties of the bolt circle, just like we did on the DRO, and it'll give you a table of numbers. These online calculators are also great if you want to do a type B circle that's rotated, because doing the math for rotating the bolt circle is again laborious and error prone. Quick aside, these tables are also super useful if you have something like an older Bridgeport DRO. Something that was pretty common was shops would have a Bridgeport from the 60s, and then in the 1980s when DROs first appeared, they would add one to it, and you may have bought one of those. Those are typically like 2-axis red LED DROs that are much more simple. They don't have bolt circle functions and other such things, but they do have the simple ability to move to any position with no backlash, which is most of what DROs are doing for you anyway, and so you can use the numbers in these tables directly on that type of DRO. The two layout methods I'm going to show both start the same way when you describe the diameter of the bolt circle on the part. I'm going to do this with dividers, and I'm going to set the radius of it using an engraved scale. If you're interested in traditional layout, an engraved scale is your best friend. It allows you to feel when the pointer is set at the right radius because the tips of the dividers settle into the engraving. You can also eyeball it on a high quality scale, but engraved scales are really nice for layout. Now, we need a way to center the divider on this circle, of course, and there's a hole in it, as there often will be. Bolt circles are generally centered on a cylinder bore or a pipe bore or something, so you don't have access to the center. We don't have any way to set the middle of our divider in there. The solution is generally some version of this. I've turned a little plug on the lathe. The closer fitting, the better, and in the same setup where I turned it, I used a small center drill to put a dimple in the middle of it, and that gives me a place to anchor my divider so I can trace that diameter. Now all we need is the intersecting lines for each of our bolt holes. I'm going to show this first on the surface plate. I've got it clamped vertically on a 1, 2, 3 block for reference. That gives me a horizontal reference on one edge of this round part. I'm also aligning the other edge of it with a second 1, 2, 3 block, and you'll see why in a second, but that is an optional step. Next, we need to set our height gauge to the center of the circle. I'm going to do that with a gauge pin. I find the top of that pin and then subtract the radius of the pin. Because this is a machined part, you could also derive the center from the radius of the part. However, usually you're not going to have a machined part, you're going to have a rough casting, and so only the center is a valid reference, and you're going to need some kind of pin or plug with which to find the center. That height gauge value now is my 0 on Y, and off camera there I've got the Machinery's Handbook open with the table of numbers, and because this is a 6-hole pattern, 2 of the holes are on the center line, so I scribe those right at what is my 0. That's easy. Then from here I scribe the rest of them using only the Y values in the chart. Because we've scribed the radius of the circle on the part, we only need one of the 2 coordinates. In this case I've chosen Y to get the others. This one's a little close to my clamp, but I managed to sneak it in there. And again, because it's a 6-hole pattern, we have a lot of symmetry. So on either side of this vertical center line, the holes are at the same Y value. The amount of shortcutting you can do like this will depend on the number of holes in your circle, but most hole patterns are even numbers, and they have a lot of radial symmetry that you can take advantage of, like I'm doing here. And of course, for the holes that are below center line, you subtract the offset in the table from the value that we calculated as the center line on the height gauge. You can't zero a height gauge, so we have to do a bunch of math to calculate the positions. But there we have a horizontal scribe mark across the circle radius at each location where each hole needs to go. Now, as you can see, depending on the radius of the circle and the number of holes, these intersections can get a little oblique, if you like. It can be a little bit tricky to see where they're actually crossing. This is still usually good enough, but if you don't like this method because of that weakness, you can forego the circle scribing and instead use both coordinates in the table in Machinery's Handbook, rotate the part 90 degrees using that other edge for reference. That's why I lined it up with both edges of the 1, 2, 3 block, and then use the other column of numbers in the table to scribe your intersection lines across that first set that we did. No radius scribing required. However, if your part is a casting or you can't use the outside edge as reference, then you'll have to find the center line again once you've rotated at 90 degrees, and this method is a lot more fooling around, and I find usually unnecessary. Now we can prepare to drill out that pattern. The next step is going to be to center punch the intersection points of all those layout lines. I'm going to do this with a small center punch, and with good layout marks, you can do this by feel. An optical center punch is also a great tool for this, but I find doing it by feel is generally accurate enough. If you look closely, you'll find some of those center punches are a little better than others, but remember, you can move a center punch. So if you see one there that you don't like, punch it again with the punch at an angle, and you can shift it around until you're happy. But horses for courses, most bolt circles are generally clearance holes, and so you don't have to be as accurate as you might think, and the holes will still line up within the tolerance of a clearance hole. Before we drill those, I'll show you the other layout method, because this is the only part where these methods differ. I've once again scribed the diameter of the bolt circle, and I'm going to punch my first hole anywhere on that line. It's going to give me my starting point on the pattern. Now I'm going to bring out my dividers again, but we're going to do this a little bit differently. This method is what I call walking the dividers. So you're going to start with a pitch circle chordal distance calculator. This is a document that I actually have up on my wall, but again, if you Google circle chord distance or bolt circle chord distance, you'll find some version of this. And what we want is that value t. That's the straight across distance between two adjacent bolt holes. If we pan down on this chart, you can see it's got a little equation for calculating t with a constant that varies by the number of bolt holes. Again, this is for unit circles. The nice thing is we're doing a 6-bolt pattern, and the chordal distance actually is the same as the radius for a 6-hole pattern. I can show you on one of the earlier bolt circles we did. I've still got the dividers set from scribing the radius, and you can see that that distance t is the same as the radius for 6-hole patterns. Super convenient, and one of the reasons why 6-hole patterns are always a good choice. Now what we do is we plant the divider in that first punch mark, we scribe the hole next to it, and we walk the divider around, scribing each hole. When you go to the next hole, you put a little more pressure on one side of the divider to anchor it, carefully walk it around, and scribe the next line. And if you do this correctly and accurately, when you get all the way around back to your punch mark, you will land exactly back in your punch mark. Another good technique is to go halfway around from each direction, because that halves any error that you might accumulate from this walking process. Once you've walked all the way around, then you can double check it by doing a little walk around, and you can see that dividers actually have a little knob on the top of them for this purpose. Walking the divider is a very common technique for lots of different layout jobs in traditional machine shop work, so they have that little knob on them to make it easier. Now, if you walk it all the way around and you find a little bit of error, you don't land quite in your original punch mark, you can at this point adjust the spacing a little bit and walk it around again. Keep doing that until your divider lands back in your original punch mark and you know that your hole spacing is correct all the way around. And then we can now, once again, center punch all of those intersection points. This method probably has the most amount of skill in it and takes a lot of practice to keep that divider from wandering while you do that, but it can be accurate with some practice. This method may not be the most accurate, but it has some advantages. It's very quick and easy to do. You only have to look up one number, that chord distance, and you can do any number of bolt circles. And you can also do type B rotated circles very easily. And this is kind of the lowest tech method. You don't have to have a rotary table or even a surface plate. All you need is a set of cheap dividers, and you can do a lifetime of bolt circles very easily. Regardless of the layout method, the next set of steps is the same. You're going to set this up on your milling machine, or the nice thing about the layout methods is that you can use a drill press or even a hand drill. You don't have to have a milling machine. The task now becomes centering the spindle on each of those punch marks one by one. I'm going to use the punch mark finder on the end of my edge finder, but there's lots and lots of ways to do this. You can use a wiggler, you can use a coaxial indicator. You can also just start with a jobber length twist drill, and they are flexible enough to kind of self-center on the punch mark. If you're going to do that method, you may want to enlarge the punch marks beyond what I've done here. Repunch them all with a couple of larger sizes of punch. Give that drill something to grab onto. The way this tool works is you feed it into your punch mark by feel and by sight. You can pretty easily tell when that very sharp point is sitting in your punch mark. Then you move the table slides until you can't feel any edge anywhere around the sides of it. And this is surprisingly accurate. Your fingers are pretty exquisitely sensitive in this way. You can easily get sub-thou precision doing this with a little bit of patience and practice. There are other ways to use this tool and also other ways to do this, but this is a method that I like. Then once again, I'm going to start with spotting drill. This is not what the jig borer manual would say to do, but this method works for me. So I spot it and drill it. Now with these layout methods, you definitely want to do all of your operations on each hole before moving on, because by far the most error-prone step in all of this is finding those punch marks. Well, and the layout, I guess, but you definitely don't want to lose any precision by trying to cycle through one tool at a time, because you'll never get the spindle exactly where it was after you ran through it the first time. So definitely cycle through all your tools one by one. It's more time consuming, but worth it for the accuracy. That's the divider walking method. I will also take the time and drill out the pattern that we did with the surface plate method, even though this step is the same, just so we can compare the accuracy at the end of all these different methods. Let's do that comparison now. I'll use the DRO one as the gold standard because really you're not going to beat that with any other methods. And I'll put a gauge pin in the center so we can get them all accurately aligned and see how they all did. These center holes, by the way, were all drilled and reamed on the lathe, so they will be accurate common reference points. First up is the rotary table method. Get that aligned, try to give you a head-on view on the camera here, and that is excellent. I gotta say, like, you could definitely get a gauge pin through all 6 of those. So full points for the rotary table method. A lot of work, much more so than the DRO, but I would say the accuracy is pretty much equivalent. Next up is the layout done on the surface plate using the hole coordinates from the book. Try to get the best possible alignment there. And once again, that is actually very good, better than I expected. You can see some slight misalignment maybe on one hole, but that is definitely within tolerance for threads, for example. You wouldn't get a gauge pin through all 6 of those holes, but we're well within tolerance on pretty much any bolt pattern you're going to need. Finally, the divider walking method of layout. That was the quickest one to do. Let's see how it did on accuracy. This is definitely the lowest accuracy. It's hard to show on camera because if you don't have the angle just right, you're getting some parallax, which is misleading, but there's definitely visible error on 2, possibly 3 holes here. You would definitely not get a gauge pin through all 6 of those. And you may be out of tolerance on threads here, but for clearance holes, we're still well within tolerance. And again, I'm not the most skilled person at layout, so with a little bit of practice, you can definitely do better than that. But any kind of pipe flange or wheel is going to bolt right up to that, no problem. And for something like a cylinder head, you're going to have a locating diameter that's separate from the bolt circle, so that's going to bolt up just fine as well. There you go. There's 4 simple ways to do hole patterns with different amounts of tooling. If you're wondering why I didn't cover your favorite method, this is far from all the ways to do it. The problem here is simple mathematics. The number of ways to do something in a machine shop is n+1, where n is the number of machinists arguing about it. But these are 4 ways that should be approachable to a large number of people, and they're all methods that I've used a lot, so I can vouch for them personally. There's also lots of variations on these that you can do. For example, if you need to do something on your drill press that's a lot bigger machine, you can make a drilling template on your mill that's more accurate and use that to get accuracy over on the drill press. Size also matters. If you're doing a large pipe flange for a refinery or something, you can also lay out the bolt circle with a protractor, which might be easier depending on how big the part is. On these little model parts that I make, that's not a practical method. But put your favorite method down in the comments below for anyone looking for more. There's lots of good ones out there. I hope this was helpful for you. Thank you so much for watching. Thanks to my patrons for making all this possible, and I'll see you next time.